On the highest derivative. Okay. On the highest derivative. Now there is a subtlety. The subtlety is the equation has to be like all the terms should have rational power, like integer power, not rational, integer power. That means if you have this differential equation, let me write on the other board. So if you have dt2, let me copy it from what I have on my note, plus dx dt this is not integer power. Okay, so you need to make it this integer, and the way you do it, you do dx dt to the power half 10 minus d2x dt2. I change sides. That's all I did. Do you follow? And now how do I make this integer? Just square it. If I square it, I get this. So now tell me what's the order and degree of this equation. Right. And degree 2. So initially, if you just look at it, you know that the order is 2, second order differential equation, but the degree, you might be tempted to write 1, but it's not true because you have this half power. So you need to basically rationalize the thing, like you don't have a square root or something. Yeah, that's the idea. But don't put too much emphasis on this nomenclature. These are just nomenclature, and you should know this, but don't put too much emphasis on that. The next thing I'm going to do, so we'll be mostly interested in second order linear differential equations and a system of differential equations. And the reason being, those are the most widely encountered type of differential equations in biology and biomedical engineering. So if I start with a brief description of the first order equations, first order ODEs, and you have already seen one, which was the cell growth problem, but in general, I can write an equation in this form, dy dt equals ft gy. So this is the first order equation, and you want to solve y as a function of time. That's you are after. Okay? And how do I solve this equation? You probably have seen such equations before. Yes? Separation of variables or direct integration, just like the cell growth problem, which is gone from the board now. What I do, I write this as dy divided by gy equals ft dt. Integration. Okay. So now on the left side you have only function of y, on the right side you have only function of time. Okay. So if gy is suitable form, you can directly integrate. In principle, you can directly integrate both sides and get the solution y equals yt. Direct integration. Okay. Suppose your gy is 1 over y square. Suppose gy is 1 over y square, and let's see what is that. And GFT is 1. Now, if you look at the equation, this is a nonlinear equation. And can you tell me why it's a nonlinear equation? Because of the y square. So this is a nonlinear equation, but you can, is that the form I used? Correct. But when I separate the variables, I get dy y square equals dt. And I integrate from between two limits. The limits I used here, for some reasons, 1 to y and 0 to time. So you get y cube over 3, 1 to y equals t. Any question so far? Is this clear? You can follow. Am I going too slow? Can I go a little faster, or this is the right pace? It's fine. So that's that. Now, there may be first order equations which does not have such a simple form. So for example, if I have this equation, dy dt plus y equals e to equals say 1. So this is also a first order equation. And do you remember how to solve such things?
Subtract y to the other side.
That's very good. That will solve this equation. But suppose I give you this. A general function of time on the right side. Then have you heard of integrating factor? Yes? So what do? You multiply sides with exponential time. Now, the left side you can write e to the power t y c to the power t ft. Let me know if you are not with me. Do you follow? So I multiplied both sides by exponential time. Now, if you do d dt of e to the power t y, first if the derivative acts on y, I have dy dt. E to the power t remains as it is. Now, if the derivative acts on exponential time, then exponential derivative remains the same function. So I get back exponential function, and y is as it is. Okay. So now the advantage of this is, this I now can write d of e to the power t y equals e to the power t ft dt. And does this look familiar to you? Can you go from here? Do you know what to do? So what happens on the left side if I integrate d of something? What is integration dx? X. So d of any function is going to give you back the same function. Okay. So I'm going to get e to the power ty equals integration e to the power t ft dt. Now, one more thing. Either you solve the equation with specified boundary condition first, so you already say solve it from 0 to y and 0 to t. That's one way of writing the solution. So you put the limits when you are integrating. The other option is first you do e to the power ty. That's option 1. And the second option is you write this as e to the power t ft dt plus c, where c is the constant of integration. Yes?
Sorry, I still don't get hang up the second step to third step there. When you first got the d dt of y.
d of e to the power ty. So
before that, yeah.
oh, here?
How you got that first term there, d dt e to the t of y.
Okay, so
It's an inverse product rule.
you have two functions, e to the power t and y.
Okay.
So you act the derivative on one of the functions, keeping the other constant. Okay, so there are two things. One is e to the power t, the other thing is y. So you need to keep one term constant and act the derivative on the second. Okay, so you act d dt on e to the power t, or say first act on y, so you get dy dt, e to the power t remains as it is. Now you act on e to the power t, what is d dt of e to the power t? That's e to the power t itself. And then y is there. Okay. So once you solve that, like you can do either put the limits, or you can keep it in terms of constant of integration. Yeah.
Question. You got integrating factor as e to the t. Could you go over how you get the integrating factors, or like wouldn't it be something like the coefficient before the y? You got e of t or e to the t because it's 1y, right?
It is because 1y.
Oh, okay.
So there are formal rules of deriving integrating factors. And you can look into books. I don't want to, because I find that a little bit complicated. So, and I don't remember those derivations myself. So if I want, I just look at the book. And for simple things, I look at the function, like differential equation, and I just try to do it myself. But you are correct that there are formal ways of finding the integrating factor.
Do we need to know this?
So if I ask you a question like that, I'm going to tell you the steps, like how do you go there, okay? So this is first order equation. Now, tell me, there are two interesting things. One is first order equations will have typically one time constant in the problem, at least in the simplest scenarios. That means if you have dn dt equals kn, nt is n0. Suppose this is negative kt. So you have an exponential decay. And what sets the time scale over which you go from something positive to 0? So this exponential decay will take you something positive to 0. So there is a time scale involved over which you decay to 0. And which set the time scale in this